everybody. Uh, Today we will discuss the different state of the stress, specifically one-dimensional, two-dimensional and three-dimensional cases. So first we will try to cover up the two-dimensional stress state, and then we will try to discuss the three-dimensional states of the stress and how the principal stresses and principal stress can be calculated from a general stress state. And finally, we will try to discuss the formulation specific to very small strains. So let us start with this analysis of the stress. So the generation of the stress actually depends on the type of loading. So the load can be applied at different direction, and when you try to estimate the load, then we can consider the area over which the load is acting at different orientation, and accordingly we can find out whether the existence of any normal stress or any shear stress it will produce. Let us look into the different type of loading. If you look into the first figure, we see that a cylindrical bar is specifically subjected to a load F, and there is some extension in one direction, but at the same time contraction in the radial direction. So this type of loading we can say that tensile loading. And if you look into the second figure, here if we apply the load but the direction of the F is just opposite, that means it's a compressive kind of load. So this type of load actually produces some amount of the stress inside the body, but we need to consider some representative volume from the body to find out the different stress state. Now if you look at another aspect, that torsion also produces some amount of the stress. For example, if we apply torque in this sample, or maybe in the cylindrical element where one side is fixed, another side is open, and it will try to produce some amount of the strain as well as the stresses, but here the strain is measured the angle of twist. So that angle of twist is the what was the initial position, and on this space what was the and final deformation and the angle between the one specific along the radial direction, that means one with respect to one radial what is the deformation over the circumference, and that we measure by the angle of twist phi. So that is also measure of the strain in this case. Just similarly we can define the application of the normal load, and then we can find out the different kind of shear stresses here also. So in this case, on this face there is application of the load, and that load is parallel to the cross-sectional area. So in this case, this angular form actually produces the shear strain, and this is the amount of the strain in this case, and shear stress we can define that load divided by the cross-sectional area. So this cross-sectional area in this case, which is parallel to the applied load, so that actually estimates the shear stress. And what was the initial case? The stress is defined in this case that application of the load divided by the cross-sectional area, but in this case cross-sectional area is normal to the applied load. So A0 is the perpendicular to the F before application of the load, or maybe that A0 may be the parallel to the application of the load. So depending on this, whether what are the nature of the stress, whether it is normal stress or whether it is shear stress, it will produce, or nature depending on the type of the load, whether it is produce the tensile load or whether it can produce the compressive load, or whether we need to apply some torsion, that actually decides the different type of stress and stress generation inside the representative volume of an specified element. So now, depending upon the type of load, we can discuss that already this stress and strain behavior with the application of the load. Let us look into this simple curve where it expresses the amount of the strain and correspondingly what is the variation of the stress with the application of the load, that is represented by this graph. That is for simple stress strain behavior with the application of the tensile load. So first up to point, suppose we start from point O, so up to point P the stress is proportional to the strain, so that means stress strain follows some linear relationship up to the limit P point, and that corresponding P point actually beside the yield stress value, and this up to this point the strain is or deformation is actually reversible, in the sense that if we remove the load at the point P, then it will come back to the original position, though, so there may not be any permanent deformation in this case. Now corresponding point P, we can define the yield stress, or maybe we can say that P corresponds to the elastic limit for this specific material. So it is known the fact for practical material that this reversible nature of the stress, or maybe exists with the very small amount of the strain, but maximum amount of the strain actually exists over the plastic zone, plastic deformation zone, in the sense that when you cross the point P and with the further deformation of the material, then it will produce the permanent deformation, and that permanent deformation is not reversible, that is irreversible, and that deformation is called as plastic deformation of the material. So even, for example, if we remove the load at some other point beyond P, and then when it is then it will not come back to its initial position, so there must exist some amount of the deformation here. So that P is generally called the yield point, that is the limit, or that point actually decides whether stress is proportional to the strain, or that means linear relationship between stress and strain exists, or some non-linear relationship exists beyond that point. So up to that point, elastic part, and beyond that point, that is generally defined in stress strain diagram, that is the plastic part is there. But this sometimes in the actual material, when you try to generate the stress strain diagram for a specific material, so yield point is basically well defined, and that can be observed. There is a smooth transition of the slope at that point. So practically we can identify that point, that means the yield point for a specific material. But certain cases that some other material, or maybe very large group of materials, actually there may not be very transition zone from plastic to plastic deformation. So that transition zone is very difficult to identify when you simply look into the stress strain diagram of that specific material. So in this case, we generally consider the offset yield point. So that offset yield point is defined on permanent amount of the strain, that is 0.002. So that point, and if we draw with this from this point one parallel line of the initial slope of the curve, then it will intersect certain point. Suppose in this case this is the point, say point Q. So that Q actually defined in this case as the yield point for this specific material. So yield strength can be defined here in this case when it will try to produce the permanent strain 0.002. So that is often called offset yield point. If we look into that most common material, low carbon steel, we can find out the typical stress strain curve, and where we can find out that there is a two yield point. One is the upper yield point and another is the lower yield point. And this point is optimum point is corresponding to ultimate tensile strength, and here is the fracture point. These are the typical points we generally observe in the stress strain diagram. But in this case, the yield strength is defined by the average stresses at the lower yield point. So there is a two different yield point in this case. So generally we consider the yield point as the average value with reference to the lower yield point, and then beyond that zone we can assume that this is the plastic deformation zone. So low carbon steel up to from here to here, it follow the linear relationship between stress and stress. So that slope actually indicates the Young's modulus in this case. Now if we do further analysis, but if we try to evaluate the different tensile properties from the stress strain diagram also, first is that toughness. Toughness actually ability to absorb energy before fracture. So for example, that stress strain diagram for ductile material actually represented by this curve A up to point B dot. So at point B dot there is a fracture happen. So the up to that point, what is the total amount of energy is absorbed by the material before fracture, then that amount of energy is a measure of the toughness for this specific material. So physical representation of the toughness over the stress strain diagram of the specific material is basically the area under this curve. So the total area under this curve actually represents the amount of the toughness. So that actually represents the amount of the energy absorbed before fracture. So that amount of energy actually represented per unit volume. So if it is possible to represent this stress strain diagram with some analytical expression as a function of stress in terms of strain, then simply we can, by integrating, suppose this is x-axis and this is y-axis, and by integrating y dx over the limit, then we can find out the amount of energy per unit volume in this case, and that is equivalent to the toughness for the specific material. So this, but how we can measure these properties? This property can be measured one specific test, that is called impact test. The toughness measurement can be done. For example, if it is a brittle material, so the deformation level, so plastic deformation zone or deformation, total deformation is very less as compared to the ductile material. So in case of brittle material, if this area represents the toughness, so which is very small as compared to the ductile material, so we can conclude in the sense that brittle material is generally having low toughness as compared to the ductile material, and the physical interpretation is the over the area. And if we simply calculate the area under this stress strain curve for different type of material, that will get the idea about the toughness of the specific material. So now we can measure the ductility also. So ductility, if we take the reference point deformation at fracture, then we can simply measure the percentage in terms of percentage elongation or in terms of percentage reduction in area. That actually the measure of the ductility. For example, in this case, the percentage of elongation can be measured what was the final length and what was the initial length with respect to the initial length, and if you multiply by 100, then that actually indicates the percentage of elongation, and that actually measure of the ductility in this case. Similarly, we can measure the ductility also in terms of reduction in the cross-sectional area. So A0 was the initial cross-sectional area, AF was the final cross-sectional area, and A0 is the initial, and if we multiply by 100, then we can find out this is the change of the cross-sectional area, or maybe percentage reduction in the cross-sectional area. That is actually the measure of the ductility. So normally that percentage elongation or reduction in cross-section area in brittle material is very less as compared to the ductile material. Now the point is that it is very much significant to analyze the engineering stress strain curve or Stokes stress strain curve, and where it is applicable mostly. So in order to study the plastic flow of the materials, it is necessary to understand the concept of the true stress and true strain, because true stress or true strain actually rely on the instantaneous deformation or stress value during the application of the load. Another way, when the stress or strain is calculated based on the original or initial cross-sectional area or with respect to initial length, then that actually the measure of the engineering stress or strain, or we can say that is the nominal stress or strain. So let us look into how this engineering stress or true stress strain are related with each other. But it is necessary to mention that engineering stress strain is basically mostly used to analyze the material properties up to elastic limit. But when we cross the elastic limit in the plastic zone, then true stress strain is more appropriate to analyze the different material properties or different characteristics phenomena of the stress strain diagram with the application of the some amount of the mechanical load to the material. So nominal stress, here we define that what is the application of the load P and what was the original cross section length. But if we define the nominal strain or engineering strain, say that change of length, L is the final length and L0 is the initial length with respect to the initial length. So that engineering strain can also be further correlated like that. So L minus L0 by L0, that is equal to L by L0 minus 1, or epsilon n plus 1 equal to L by L0. So this is the correlation between the strain with respect to the original length and the final length when we are considering the engineering strain. Similarly, when we try to find out that true stress value, this true stress value actually defined by the ratio of the instantaneous load with respect to instantaneous cross-sectional area. So that means the sigma t, that is a symbol we have used here to represent the true stress, that is P divided by area. P is the applied load and A is the corresponding area at a specific point. Since during the plastic deformation there is a change of the cross-sectional area, so it is justifiable to use that what is the area of the cross-section at specific point and what is the load at that specific point, that represents the true stress in this case. So now we try to find out that what is the relation between the true stress and true strain. Let us look into this. That this we have defined that true strain this would be engineering strain so this would be engineering strain. So engineering strain is the change of the final minus initial length with respect to the original length, and that is the relation. But when you try to estimate the true strain, we assume that there one element form of length L, and at this instance the increment of length is dl. So at this point the increment of the strain d epsilon elemental strain, that is true strain actually, that can be defined by increment length with respect to at that point what is the original length. Now when you try to estimate the absolute value of the true strain in this case, that we can do the integration over the elemental true strain, and this is the integration form, and that assume that there is a deformation happens from initial length to, suppose this was the initial length to final length, so that limit starts from initial length L0 to final length LF, and finally it comes logarithm LF by L0. So this is the expression of true strain in this case. Now we can further correlate this thing, that so 1 plus then we can find out the LF by L0, which is equal to engineering strain plus 1. So 1 plus engineering strain is equal to LF by L0, that is equal to exponential of true strain. So then it's finally come that true strain equal to logarithm of 1 plus engineering strain. So this is the relation between the engineering strain and true strain. But if we further expand these things, 1 plus logarithm 1 plus x equal to x minus 1 by factorial to x square, like this, and if the amount of the strain tends to 0, then we can find out the true strain actually tends to engineering strain. So that means the small strain cases, the value of the engineering strain and true strain is almost equal, there is not much difference. Now we try to find out the other correlation when you try to in terms of the true strain or engineering strain. Let us look into that. So during deformation, mostly there existence of plastic incompressibility, that means there may not be the change of the volume but change of the dimension of a specimen. So in that sense, suppose the dimension was L1, L2 and L3, and that is the final dimension, and initial dimension was L10, L20 and L30. So then change of the volume, final volume minus initial volume, is basically in this case suppose 0 to maintain the plastic incompressibility. So if we assume that change of volume, there is no change of volume, so we can further decompose in the terms of logarithm form. Then we can find out that each component actually represents the true strain. So maybe true strain component second component and true strain third component, or maybe we can say x, y and z, that is actually 0. So this is the relation when there is no change of the volume during the plastic deformation, so that true strain actually holds this relation. Now similarly, true strain equal to logarithm of 1 plus engineering strain. So this in terms of engineering strain we can find out equal to 0. So that means this is equal to 1. So that's the relation actually holds in terms of the engineering strain when we assume that there is no change of volume during plastic deformation. Now we can do further calculation also. Suppose there is a cylindrical element, and in that element first two dimension L1, L2 is equal to area A0, and L2 dot L1 dot equal to A, that is the final cross section area after deformation. So this should be maintained volume consistency, so there is no change of volume. So volume remains the same before deformation and even after deformation, but the dimension change, that means cross section and another length dimension actually changes in this case. then we can find out that A0 by A is L3 dot by L3, which is equal to the exponential of true strain, and that A equal to A0 into exponential of minus e to the power epsilon to the power t. So that actually represents the relation between the cross section, initial cross section and final cross section in terms of true strain. So we can do further calculation of the stresses. So engineering stresses is defined by the load divided by the original cross section area, or we can represent other way. The true stress is basically the ratio of the instantaneous load and the cross section area at that point. Then we can put the expression of this cross section area, and we can find out that the relation between the true stress and engineering stress in terms of the true strain, and or we can find out that engineering true stress equal to in terms of engineering stress and engineering strain. So this correlation between engineering stress and engineering strain is very much helpful to do the further calculation of this. Now when you try to represent the stress strain diagram of a specific material, then we can obtain the engineering, most of the cases we obtain the engineering stress strain diagram, in the sense that we are using the engineering stress and engineering strain which takes into consideration the initial or original length or original cross section to calculate the stress and strain value in this case. Now this is the relation of the stress, engineering stress and engineering true stress, and this is the relation we use between the true strain and engineering strain. Now if we put into that up to the yield point, there is a more or less the true strain part and engineering stress part is almost equal, but practically this up to this common point, actually this amount is the very less amount, so very less amount of the strain actually. So in this case engineering stress and true stress and engineering strain and true strain is almost equal up to that point, but with the when it just enters to the plastic deformation zone, so there is some variation, there is some deviation of the engineering stress strain curve and the true stress strain curve. If you look into that, true stress strain curve is, see, always it is, there is an increasing nature, stress is actually increasing nature when you consider the true stress strain diagram. But in case of engineering stress strain diagram, there is an optimum point that is called ultimate tensile strength, and after that necking happens and there is a reduction of the stress value, and finally rupture happens or fracture happens at a specific point which is less than the optimum stress value. Since the true stress strain curve consider the instantaneous area, so with the in the plastic zone with the further deformation of the material, there is a reduction of the cross section area specific to in the necking zone. So when there is a reduction of the cross section area, then the stress value actually increases. That's why the true stress strain curve always we getting the increasing trend of the stress value with the further deformation. Now if this point actually represents the ultimate tensile strength with reference to the engineering stress strain curve, now from that point we can, but this point may not be on the same strain level in case of true stress strain curve. So there is some deviation of the actual actual ultimate tensile strength with respect to engineering stress strain curve, and that point is different in the true stress strain diagram, because if we look into the relation between the engineering stress and true strain, we find out that strain value, actually the strain value is logarithm of 1 plus engineering strain. So if this is the engineering strain value, so 1 plus engineering strain value, and if we consider the logarithm scale, then actually true strain value is less than that of engineering strain value. So that's why this point is shifted to other side, lower side. At the same time, if we consider the true stress value, actually it is, since this component is more than 1, so true stress value is always greater than the engineering stress value. So the stress value actually more in this case. So this is the amount of the stress is more corresponding to that point, and this is the amount of the strain corresponding to this, less corresponding to the ultimate tensile stress with reference to the engineering stress symbol. So it is by using this relation, engineering stress and true strain, or engineering strain and true strain, we can predict the true stress strain diagram with reference to the engineering stress strain diagram. Now, if the one situation arise something like that, if we try to deform the material or uniaxial deformation of a specific material up to certain point, say point A, it follows a elastic deformation. Beyond that, there is a nonlinear, if you see the nonlinear shape of the curve, and up to point B, there is a nonlinear deformation, and that deformation actually enters the plastic deformation zone. So, but at the point B, when there is a release of the load, then the specimen will come back to the point C. So that point is, so at point C, but if we see from the diagram, so there is some existence of the permanent amount of the strain. So that amount of the plastic deformation actually exists within the sample, that is not recoverable, since it crosses the plastic limit and it enters the plastic deformation zone. Now, what way generally theoretically this B comes to the point C, but what are the way it is following? So in this case, from B to C, it is following the path which is the parallel to the initial slope of AB. So basically parallel to the line of OA. In that path it will try to follow. So to following this path, now if we project B, actually when we deform up to point B, so up to OD is the total deformation or total amount of the strain. But after removal of the load, actually the material comes back to the point C. So there some amount of the recovery happens, that is the amount of CD. So that CD is basically called the elastic strain recovery. So this kind of behavior is observed when material follow the mechanical deformation, in nature like glass to plastic deformation. So that CD we can easily calculate the amount of the elastic recovery zone if you know the yield point values, and we know the Young's modulus also, because Young's modulus OA, that is represents the slope, and this path BC actually parallel to this slope. Now again from the point C, if we deform the material, then it will goes back to, it will start yielding at point B, and then with further deformation it is follow the plastic deform path which is in the plastic deformation zone. So in the second time during the reloading, actually the B point actually acts as the yield point in this case. So there is a change of the yield point during the second time deformation from point A to point B. So that actually happens due to the strain hardening mechanism for this specific material. Now we coming back to from the one unidirectional stress or strain analysis, what is the difference between the engineering stress and engineering strain. Now we come back to that point of stresses at a point, how we can define the stress. So when a body is loaded by normal or shear stresses, we can consider any point in that body as a stress element. This stress element can be depicted by a two-dimensional form, or more correctly by a cube in a three-dimensional form with the stresses acting on it. For example, if we consider this element, there is application of the load, this is a beam, but we consider there is no variation of the any load or stresses along the normal to this beam. So this is the application of the load F. This is the x direction, and if we consider small elements, specifically in 2D analysis, we just pick up one square element, and that square element we can represent the what are the different stresses is acting on that element. Here if you see with the application of the load, so there may be some normal stress will be acting, that is acting normal to the edge. So that here in this case it actually produces the bending stress, but it is normal to this edge. But at the same time it will create the shear stress also, that is acting parallel to the edges. So that shear stress we can define here. So with the combination of normal stress, that means bending stress, and shear stress, we consider this as a stress element, and then we can further analyze the amount of the maximum stress or minimum stress like that. Similarly, this is a round cylindrical element. It is subjected to a torque T, and at the same time it is subject to a normal load F, T and F. Now if we consider one element on the surface, then it can be represented on this element that it is subjected to simply the axial load due to the application of the load F, but at the same time due to the application of the torque T, it is subjected to some, or it will try to produce some amount of the shear stress. And how it represents this element, it is like that. We consider first a square element, and within that element there is a axial stress is acting and at the same time circumferential stress also acting, but at the same time there may be the shear stress on the edges. So this is the description of a one body is subjected to different kind of loading, and that we can represent this loading in terms of the small element and what are the different stresses is acting on that element. Specifically the two types of stresses acting here, one is the normal stress, another is the shear stress. So now we can further analyze the stress state. Now we consider the plane stress condition. For example, the third stress in the third direction is basically 0. So with the plane stress components, this is the element, and we define this as the x-axis, this as the y-axis. Now along the x-axis, positive x-axis, the stress is defined by sigma x, which is considered with this configuration as a positive. Similarly, this direction, this sigma is also considered as a positive in this case, and similarly sigma y is acting along this positive y direction. So this is sigma y, and this notation tau xy and tau yx, in this case we can consider as a shear stress and is considered as a positive value. So we will further discuss about the sign convention with the positive negatives of the shear stress or normal stress, and I think after few slides. Now here is basically two normal stresses is acting along x and y, that is sigma x and sigma, two different normal stresses, and the one shear stress component is acting because we are assuming there is a not rotation of the element. So tau xy equal to tau yx. So convention of this is like that, with the direction as well as how we are writing the tau xy, and this is the tau xy, and this is also tau xy, and other cases tau yx, and this is the tau yx. So but in this case tau xy equal to tau yx. So this is the 2D representation of the stress state. Now what will happen if we try to represent the stresses with a certain specific angular or certain oriented. So this is the three-dimensional stress state. First figure, 3D view. If you look into 3D view, then it will be very obvious that normal stress is acting on this face, and shear stress is acting parallel to this face, tau xy. So in the sense tau xy, so that means it is the second y is the that represents the which y direction, positive y direction, and it's a, and other component is the x. Similarly tau yx, So it is acting along the yx, the second component along the direction x, and this is acting over the face. And similarly, the sigma x is acting normal to the sigma is the another the sigma is acting normal to the y-axis. So from this is the typical 2D view that, and now we'll try to explain that if there is a orientation with respect to x-axis of angle from the theta, and then it will define the new axis with the x1 and y1. So then with respect to the x1 and y1 axis, what are the different stress, that means normal stresses and shear stresses acting, and how we can correlate with respect to the original axis, that means sigma x, sigma y and tau xy. Now if we take the transformation of the stresses or the taking simple system, how this transformation can be done with some orthogonal axis. Suppose the three-dimensional view is this is the element and x, y, and along the direction y, so there is a acting of the load is Fy, and similarly normal to the x-axis the load is Fx. Now we consider a plane whose normal y dot is at angle theta with respect to y. So we constitute one plane, but that plane is basically parallel to the z axis. So we are not considering any variation or component of the stress along the z direction. So that plane we define in such a way that y-axis actually y-axis transformed to the y dot, that y dot actually normal to that plane. So and that plane, that y dot and y is making an angular form theta. Similarly we transform the x dot, which is another orthogonal axis with respect to y dot, as x dot. So we define the different stresses here. First we define the stresses here, sigma y equal to Fy by Ay. So that was the original, so that is the stress. Now Fy dot, that means transformation of the force with respect to the along the y dot direction, that Fy dot can be represented Fy cos theta. Similarly the area of that plane Ay dot can be represented Ay by cos theta. Now the normal stress along the y dot direction, sigma y dot, or maybe we can say sigma y dot is equal to Fy dot by Ay dot. That means along that y dot direction what is the load or what is the force, and with this what is the normal area with respect to the y dot axis. So if we put that Fy dot here, Fy cos theta divided by Ay by cos theta, similarly it is find the Fy by Ay cos square theta, and Fy by Ay we already defined, that is the sigma y, that is the reference to the initial position. So sigma y cos square theta. So the geometrically if we look into all these things, so it is possible to transform from one component of the force, and that the new stress value, so that stress value is defined with respect to y dot axis in terms of the y axis, and that angular relationship between y and y dot in terms of theta. So this is the expression. Similarly we can find out the shear stress as well also. So tau y dot x dot, that means what is the shear stress is acting on this plane, so on the defined plane, that means it is definitely acting the parallel to that plane. So in this case, or notation we can use this tau y dot x dot, which is similar notation of sigma y dot x dot, that is equal to the area acting normal that along the x dot direction. So along the x dot direction, that means Fx dot, the component is here Fx dot, and what is the area? Ay dot, that is the area. So Fx dot is actually Fy sin theta. Similarly, A dot y, Ay dot is Ay by cos theta. Then we can find out that shear stress is actually sigma y cos theta sin theta. So with this transformation or some geometrically we can find out what is the stress state at the some other axis or some other axis system, which is analogous to the or with reference to the initial axis system. So here now how we can define the sign convention, shear stress and normal stress here. So if it is defined as the x and y axis like that, now that normal if sigma xx greater than 0, then we can consider this as a positive. But if we consider this sign convention tau xy, in this case this is the representation of tau xy. So in this case it is positive, in this case it is negative value, but we can define in such a way that tau xy, so it is so direction is like that, it is the positive x, this side is the positive x, but here opposite to the y, so negative y direction. That's why this direction actually produce the negative value of the shear stress. That is the representation of the shear stress. If it is possible to show the shear stress is like this, then we can say tau xy is greater than 0. That means this symbol actually represents the positive value of the shear stress. Similarly, we can find out this is also negative. This direction also represents the negative value, but on the opposite side, this actually represents the positive value of the shear stress. So with the axis system, we can define we can decide whether it's a positive shear stress or the negative shear stress, or what is the positive normal stress value or negative normal stress value with this sign convention. Now we come to that point, stress transformation in general form. So stress transformation is a way to describe the effect of the different combined loading conditions, and on a combined loading condition that actually act on a stress element and at any orientation. So at any orientation, if there is application of the load, that we can represent the one stress element, and within the stress element different orientation we can find out the new values of the stress or strain with if we know the actual geometric orientation of the element. So from the geometry and the equilibrium conditions, so further we can, if we follow that summation of f equal to 0 or moment equal to 0, so that is actually represents the equilibrium condition, and from the geometry geometry condition we can further find out the stress value at the different axis system. For example, in this case, this is the initial definition of the stress state on a square element, the sigma x, sigma y, sigma and tau xy and tau yx. So in the sense here we show the direction in such a way that all actually represents the positive value. There is no negative value in this with this specific representation. Now suppose there is a orientation at angle theta, and that will produce the two orthogonal axis system x1 and y1 with the theta, and on the x1 and y1 axis there is a representation of the stresses like x1, sigma x1, sigma y1, tau x1, y1, tau x2, y2, like that. So in this case, on the new axis system or the transformed axis system, we can find out the sigma x1 equal to, in terms of the sigma x, sigma y, the angular form, and in terms of tau xy. Similarly, we can find out the tau x1 y1 in terms of the sigma x, sigma y and tau xy. So we use the geometric configuration, and that means we know the angular what is the orientation angle theta, and we can find out the sigma y1 also. So this angle, from now if we cross check it in such a way that suppose theta equal to 0, so when theta equal to 0, then all this expression should come back to the position like that equal to the what was the initial position. So this position will come back again when theta equal to 0. Now if we put it cos theta, cos 2 theta, cos 0, 1, this is 0. So if we add this thing, so it becomes sigma x. So that is true also. Similarly, tau x1 we can investigate also, simply putting theta equal to 0, it will tau x1 y1, it should be equal to tau xy. Similarly, sigma y1 will be equal to sigma y if theta equal to 0. So this is just cross check it with the expression. Now further we can analyze this thing, that given stresses at any angle, we calculate stresses at any arbitrary angle. So that means we can define one angle theta, and then with that angle, with the orientation of the theta, and we can define one orthogonal axis system, and we can represent the different stresses also. Now if we consider that any arbitrary angle theta, now how the stress and strain actually varies in this case. So even if we consider the uniaxial loading condition, so if there is a application of the only uniaxial loading condition, that means there is only single stress state there, sigma x. Now if we try to find out the state of the stress in any angular form, which is theta not equal to 0 degree, then we can find out, then we will be able to find out that sigma y and shear also acting on this element. Now if any of the transform stresses at angle theta exceeds the material's yield point, then the metal will fail. So even it was loaded by the lower stresses also. So we need to analyze the variation of the stresses at different angular form. Let us look into that figure. If we see, this is the variation of the sigma y, red sigma y, and if we see at different angular form sigma y, similarly we can find the variation of the sigma x also, and tau x dot y dot. So that x dot y dot actually represents the new system of the axis, and that is defined with respect to the orientation theta with the initial reference value, that means initial x and y axis. Now if we see, there is a repetition of the stress state, so this point again repetition of the stress state after hopefully after 180 degree, and similarly we can find out this thing. So this is the individual variation of the two normal stress component as well as the shear stress component. So it is also important to know that what may be the, with this variation there must exist some certain maximum amount of the stresses or minimum amount of the stresses, and location in the sense that at what orientation all these stresses exist, that is worth to investigate further, looking into this variation of the stresses with one specific angular form. But before that, we look into an example that of the stress transformation, how we can is practically necessary when you try to analyze some problem. So this problem actually defined that a rectangular plate is formed by welding the two triangular plate. So this is one triangular plate, this is another triangular plate, and the dimension is given, and weld it, and then we can find out one rectangular plate. Now it is necessary, the plate is subject to the tensile stress of 500 megapixel in the long direction, means this direction 500 megapixel stresses acting, and the compressive stresses is acting on other direction, that is 350 megapascal. Determine the normal stress acting perpendicular to the line of the weld line. So if we define this as a x-axis and this as a y-axis, now it is something like that. The weld joint actually exists along this, so it is having some angular form, angular orientation theta. Now we need to find out the normal stress acting perpendicular to the line. So now we need to find out normal stress perpendicular to the line and the shear stress acting parallel to the weld. So this may be the shear stress. So if this is the axis system is x1 and this is axis system is the y1, so this is x1, this is y1, then we need to find out the amount of the stresses with the orientation angle theta. So theta can be calculated with the dimension that 3 inch and 5 inch. From here we can easily find out the theta, And then we can find out the new axis system x1 and y1. So sigma x1, sigma y1 and sigma x1 y1 simply using the transformation equation in terms of theta and in terms of the initially defined sigma x and sigma y. But here we need to find out shear stress tau xy, but it is mentioned that the normal stress acting perpendicular to the line. So that means that actually represents y axis. So we need to find out the sigma y1. So sigma x1 may not be needed in this case. So this problem actually explains that transformation of the axis is helpful to find out to solve the different kind of problem. Now, since we observed that there is a variation of the different stresses with respect to the orientation angle theta, then there must be important to know what may be the maximum or the minimum normal stresses exist, what are the maximum shear stresses exist, and orientation over which or at which this maximum or minimum stresses occurs or maximum shear stress exists. So all these maximum cases, the maximum normal stresses actually called as the principal stresses, and that with a specific orientation that is defined by the sigma 1 and sigma 2. And maximum shear stresses we can define the tau max if we analyze the variation of all these stress steps in a two-dimensional case. Actually the equations for these cases are found out from the stress transformation equation by differentiating the d sigma by d theta. Theta is the angular form equal to 0. From here we can find out, and with some algebraic manipulation we can find out all these maximum and minimum stresses values. So what are the, or that is specifically called the principal stresses. So what are the principal stresses? All these cases, let us look into that part. So first is the sigma average value. Sigma average value we can simply define the sigma x plus sigma y by 2. Now tan 2 theta p here. So theta p actually the planes of principal stresses. So what theta p planes of principal stresses, actually the two planes exist. One is the theta p1 and another is the theta p2 with their 90 degree apart, but no shear stresses acts on the principal stresses. No shear stresses act on the principal planes. So we can define the principal plane over which the principal stresses acts, but on that plane there doesn't exist any shear stress value. So with that we can, with the manipulation we can find out that sigma 1 2, that means principal stresses 1 and principal stress 2, will be able to find out sigma x plus sigma y by 2 plus minus of sigma x minus sigma y by 2 plus tau xy square. So that theta p actually find out that theta p actually calculate the orientation of the axis over which the principal stress exists, and that is with respect to the initial stress value, or that means with respect to the xy. So we can find out the principal stresses in this case by using this formula, and the the planes of the principal stresses we can define from here also if we know the initial stress state. Similarly, we can find out the planes of the maximum shear stress. The maximum shear stress on the planes exist at the theta s1 and theta s2. Again, there the difference between theta s1 theta 2 is a 90 degree, but it is 45 degree offset with respect to theta p. Theta p is defined by the planes of the principal stresses. So here, and so the theta can be calculated from here, normal stress test and the initial stress state, and maximum, the tau max IP is the maximum in plane shear stress, that can be defined here with this formula, and finally the maximum amount of the shear stress is the basically the magnitude of the difference between the principal stresses and 50% of that. So these are the principal stresses value in case of two-dimensional stress state, and all this formulation we can find out the amount of the principal stresses and their orientation with respect to the initial defined of the axis system. Now Principal stresses represents the maximum and minimum normal stress, that is fine. At the point, at the orientation at which principal stresses act, there is no shear stress. So from the graphical form we can find out the variation of the different normal stresses and the shear stresses. We can find out that one point that actually indicates the principal stress value, the maximum normal stress value, and on this maximum normal stress value the shear stress is equal to 0. Similarly, there is another phase of 90 degree, so we can, this point also principal stresses exist but shear stress equal to 0 at this point, and one principal stress, that is minimum stress value, so that also exists, sigma 2. In this case there are two values here, 1 and another case is the 1. So if we look into that, at the two different orientation, theta p, another orientation theta p which is 90 degree apart, so along that orientation the principal normal stress exists, in the sense the maximum stress and the minimum stress. Here also maximum stress and the minimum stress exist at the and orientation of the theta p. But what are the amount of the shear stress value? So if you look graphically, the shear stress exists at this point, maximum amount of maximum shear stress, but the amount is the positive and it is the negative, magnitude is the same but maximum value. But so on the at the orientation at which the maximum in plane shear stress act, the average normal stress acts in the both normal directions. So corresponding to the maximum shear stress value, this is the average value, normal stress value actually acts at this point. So but here the orientation with respect to the theta p is basically the, so theta p, the orientation is 45 degree with reference to the theta p. So at the in plane maximum stress, so the element acted upon by the maximum in plane shear stress is oriented 45 degree from the element acted upon by the principal stress value. Now we will look into the few example problem to bring the clarification of the application of the all the stresses, or how we can find out the maximum minimum principal stresses. Now if this example, at a point on the surface of a machine component, the stresses acting on the x phase of a stress element sigma x equal to 45 megapascal and tau xy 30 megapascal. Now what is the allowable range of the values of the stresses sigma y if maximum shear stress is limited to 34 megapascal? So now we know the maximum in plane shear stress, this is the expression, and we have the sigma x value and we have the sigma x, and we know the shear stress value tau xy acting on this case. Now we need to maximum allowable shear stress limit also given. So from here we can find out the sigma y in terms of sigma x, tau xy and tau 0, and we can find out the numerical range of the sigma y by the knowing values of the sigma s and tau xy. But to be noted that sigma y cannot be 0 because at some angles the combined effect will raise the shear stress value above 34 megapascal. That is the limiting case of the shear stress value. So here we can find out the limit of the stresses value. Now we look into that Mohr circles, which is very basic things, but the stress analysis specifically is very much useful for the two-dimensional cases. So physical significance of the Mohr circles for plane stress is established. It may be applied with a simple geometric consideration. Critical values are estimated graphically or can be calculated. So this is the typical values of the typical picture of the Mohr circle. Here the Mohr circle, how we can draw the Mohr circle? So define the axis system and origin O, this this origin, so assume that along the x-axis the stress is represented, along the y-axis the shear stress is represented here. Now here we need to find out for the first the center point, and from the center point we can depend along the radius r. So over the radial we can draw one circle. So that on that circle, that point OA actually represents that, with reference to the origin O, the OA actually represents the maximum values of the normal stress, and OB actually represents the maximum minimum values of the normal stress, and along that direction this diameter this so maximum shear stress is along that direction, that is the equal to the radius in this case. Now stress state, how you can represent the stress state? One specific, suppose we have defined the x-y axis system, I think. Suppose here the initial stress state we define sigma x tau xy with this notation or with this configuration. Now at the theta p, so with the orientation there exists the principal stress state. So now how this principal stresses can be represented or can be extracted from the Morse circle. Now that point x is basically represent the coordinate of point x. On this coordinate is basically x equal to sigma x, the normal stress value, and minus of the tau x1, so negative values of the shear stress, because the y-axis actually, this side is the positive y-axis that represents the shear stress value, opposite side is the negative shear stress value. So this is the simply coordinate, the sigma x, sigma y, and this angle actually represents the theta p. So since here is the angle theta p, but when you try to represent the Morse circle over the 360 degrees, so here the Morse circle will try to represent the 2 times of the angle, so 2 theta p, and this point exists the stress state x, and y point actually represents the y component sigma y and corresponding the shear stress value. Now with this configuration, so that is the, so you can say that we can say that x y actually represents the initial stress state, and when it is oriented to certain angle from theta p, so at that orientation theta p, the stress state actually represents the maximum values of the shear stress or minimum values of the maximum values of the normal stress and minimum values of the normal stress. So with the orientation of the theta p, and that theta p is, we draw on theta p angle, and that we present the maximum stress state or maximum principal stresses on the line on the axis actually O sigma, that axis system. So basically at this x point, the coordinate point indicates this amount is basically sigma x, and this amount represents the shear stress value. Similarly, this amount represents the sigma y, and this amount represents the tau xy. Now from the known state of plane stresses sigma y, sigma x and tau xy, plot, first we need to find out to plot the points x and y and construct the circle centered at C. So first is the, how we can find out the center at C? The average value, sigma average equal to sigma x plus sigma y by 2, and then radial distance can be represented by sigma x minus sigma y by 2 square plus tau xy square. So in this case, that C is basically from here to here, the center point, that is actually represents the average stress value, normal stress value, and that represents the point C. Now with respect to the point C, we need to define, we can define already the x and y point, and now with reference to the point C we can draw one circle. When you drawing one circle, then sigma max up to OA actually represents the amount of the sigma max, and OB the sigma mean in this case. Now the principal stresses are obtained at A and B or sigma max and sigma mean, which is equivalent to the average value, that means OC plus minus OA, that means average value plus minus the radius in this case. So tan 2 theta p easily calculated from the coordinate of the stress state. So tan 2 theta p is the twice tau tau xy, this amount divided by sigma, and so this distance actually represents the half of sigma x minus sigma y. So tau xy divided by half of sigma x minus sigma y, that is twice tau xy by sigma x minus sigma y, that represents the tan 2 theta p. That means this represents the stress state at this point. So the direction of rotation OX with respect to this figure, the direction of rotation OX to OA is the same as CX to CA. So from CX to CA in the Morse circle, but which is in practical it is from OX to OA. Okay. So this is the typical Morse circle description. Now Morse circle uniquely define the state of the stress at any other axis, but maybe other orientation. For example, Morse circle can also be drawn if there is an initial orientation of angular form theta with respect to x axis. Now this is the with some other axis system, say x dot y dot. Now with respect to that, we need to find out what is the maximum stress and means minimum stresses that can be represented by the Morse circle as well also. So in this case, the initial stress state is deep. So x y actually represent the stress state with respect to the axis system small x small y, the stress state. Now but x dot y dot, we need to represent the stress state to draw opposite angle 2 theta here, and then x dot, and we define the x dot and y dot. And finally, if the principal stress exists with respect to theta p, then that angular can be twice theta p, and then accordingly looking at the coordinate, finding the radius, we can draw the circle, Morse circle in this case. Now this is the Morse circle for the simple axial loading. Representation of the Morse circle for axial loading, that sigma is there only one stress, one kind of loading is there, so only one along the x-axis there is only one stress, sigma x, but sigma y and the shear stress is absent here. Then Morse circle can be drawn like that. For the stress state, it's that radial distance cy, that means sigma x, sigma y, and tau xy equal to p by twice p by 2a. So basically sigma x equal to p by a, sigma y t by, when there is a existence of the maximum stress value, then it is the half of the initial value, so p by 2a. But in this case, the maximum sigma x, sigma y, and tau x all are same. So similar way we can find out the stress state here. First we need to find out what is the cy using the formula, and then radial distance, C is the center point, and radial distance, if you look into that, maximum value is there, but minimum value is 0 in this case. Minimum value there is 0, and shear stress value, which is equal to the radial distance, but the CD is the radial distance, or maybe radius, so that radius is the half of the sigma x value. So that are the maximum shear stress value in this case. Similarly, Morse circle for the torsional loading also. So there exists only the no normal stresses, only the shear stress component is there. So in this case, the shear stress component, the state of the stress can be defined like that: sigma x, sigma tau sigma, but maximum values sigma x and sigma main. At this point, the tau xo equal to 0. So shear stress maximum equal to tau c by g, but maximum and minimum value with respect to the origin is the same in this case. So construction of the Mohr circle, just try to look into this thing, that suppose this is the stress state, and first we try to draw the Mohr circle from the stress state, that we define the axis sigma and tau, and in this case first the stress is sigma x equal to 50, sigma y equal to, with the notation sigma y, that means compressive stress is there 10 megapascal, and here with the notation the shear stress is positive 40. Now average values of the average stress value sigma average equal to 20 megapascal. From here we can find out the stress rate at the x. So since the sigma x is given 50, so the x can be drawn on a certain point, the distance 50, but center point is 20. So CF can be calculated as 50 minus 20, 30, and Fx is the, at this point, the state of the initial shear stress state is equal to 40 megapascal. So Fx equal to 40 megapascal. From there we can find out the R Cx 50 megapascal, and then we construct the circle. Then you can find out that maximum shear stress value of principal stresses in this case. So maximum shear stress value is basically OA. OA is calculated as 70 megapascal, and minimum equal to OB. So OB equal to, I think, minus 30 megapascal, and tan 2 theta p. So this angle is the 2 theta p, is basically from the, we can find out the geometry 40 by 30. So theta p is equal to 26 by 6. So this is the, so first looking into the average stress value and then find out the radial distance, and looking into the stress state we can find out the stress state point x and y, and from that point we can draw the circle by identifying the center point. So this is the way to construct the Mohr circles from the stress state. So now principal stress x is theta p, and here we see that maximum and minimum, because minimum stress is the compressive and the maximum stress is the tensile. So this is the representation, and that exists over the angle theta p, so which is 26.6 degree here. But maximum shear stress value we can calculate in this way, that so this is the stress state where is the principal stress exists, so no shear stress, but with respect to the offset of 45 degree with respect to the theta p, at that point there existence of the maximum shear stress value. But in this case, from the Mohr circle, how we can find out this thing, that maximum shear stress value actually represents the CD, and because this is the radial distance, so CD is actually 50 megapascal, and since x, y was the initial stress state, x and y we defined at the initial stress state, and 2 theta p along that direction, along the this axis we represent the maximum principal stresses value, and further 45 degree offset, so that means here 45 into 2, 90 degree, so offset at this point actually represents the point D, actually represents the maximum stress value. So we can easily find out that theta is equal to simply theta p by 45 degree. So the tau max equal to R here 50 megapascal, and stress value at this point sigma dot equal to average value 20 megapascal. So far we have discussed that two-dimensional stress state, and what is the difference between the engineering stress and true state, or relation between engineering state and true state, where it is applicable, and finally we come back to that two-dimensional stress state and representation of the stress state using the Mohr circle, and how we can analyze or how we can find out the principal stresses or normal stresses and shear stresses, and these all are the basic analysis of the stress in case of two-dimensional. So this transformation of the stress is actually useful for the further in the plasticity analysis or further problem when you try to analyze the crystal elasticity or crystal plasticity problem. So hopefully this class will give some basic idea of the stress analysis, and now next class I will try to analyze the three-dimensional stress state, and specifically the more important thing is that the transformation of the stress from one axis to some other axis. So thank you very much and for your kind attention.